Dear students, in this video we will be solving some more problems on Cauchys residue theorem. As an example, let us consider this problem. Suppose we have to evaluate this integral 0 to infinity cos ax divided by 1 plus x square dx. First of all, I make a change in this integral. I will extend its limit from, say, suppose you have, so this, look at this situation, this is 0, it is plus infinity minus infinity here, an integral from 0 to infinity can also be written as integral from minus infinity to plus infinity divided by 1/2, provided there is a caveat, provided the function, the integrand, that should be an even function. Since cos ax is an even function, so is 1 plus x square, both are even functions, hence we can do it here. We can extend this limit from minus infinity to plus infinity cos ax divided by 1 plus x square dx and 1 by 2 here, half of this. Now this integral has, say, it is almost similar to the previous integral with one difference, that is you have cos ax in the numerator instead of 1. In our previous integral we had minus infinity to plus infinity 1 by 1 plus x square dx. Now we have this here, this integral, we have cos ax in the numerator. How do we solve this? We have to such integrals which have cos ax in the numerator or sin ax in the numerator, they usually demand that they should be handled through their these exponential equivalents. What does that mean? That means, instead of cos ax, I will first evaluate this integral 1 by 2 minus infinity plus, or simply let me write this thing, I dash equal to minus infinity to plus infinity e raised to I a x divided by 1 plus x square dx. Why so? Why we do this thing? Because when we suppose what we do, let us do one thing. Let us first try with this itself to see where is the problem and what is the nature of the problem. We try it with this, we change this in order to utilize Cauchys residue theorem. We change this real integral into it is equivalent complex contour integral. That contour integral is, say, suppose I dash is equal to, leaving behind this 1 by 2, it is equal to minus infinity to plus infinity. Sorry, not in contour integral, since that is contour integral. This means that it is a line integral evaluated along a suitable this closed curve contour, and this is what you have to evaluate there, cos ax by 1 plus x square dx. Or if you retain this 1 by 2, okay, without causing any this confusion, I have to evaluate this. Since it is contour integral, complex integral, I have 1 plus x square dz. This is the situation. Now, as usual, as you know, we need a suitable this closed curve or contour. How do we decide this contour? We decide it by looking at the singularities of this function. This function, as usual, cos az doesn't have any singularities. It will not have any singularity. Because of this, the function will not have any singularity. However, 1 by z square, as we examined it in the previous video, we saw it has two singularities, one at z is equal to I, another at z is equal to minus I. minus I. So what we do, we choose the same this closed path or contour as we did in previous video, that was from minus r to plus r, from minus r to plus r first, and this was I here, I and minus I, minus I. So in order to evaluate this integral, this integral, in order to evaluate it, what we have, we know we need residue of this, that calculating that residue is not a problem. That is okay, we can calculate that. But then when we decompose this integral, I dash equal to 1 by 2, and then we decompose this integral, which goes from minus r to plus r. We split it into two integrals, one from minus r to plus r, a real integral with cos ax divided by 1 plus x square dx. Then another cr, that is integral from this along this cr, along this semicircular arc. This integral cr is equal to, cos ax, cos az divided by 1 plus z square dz. The integral is, I use this x from minus r to plus r. I have already explained it in previous question. And then you see, there is no problem. What is the problem? You know that ultimately when we find this integral, it depends upon this factor, cr, this loop integral along this. If r tends to infinity, if this loop integral goes to 0, then we will have this as, we will be left with this. If it does not, then we cannot solve this. We cannot say that I dash is equal to this. So let us examine whether it will go to this term, cr cos az divided by 1 by z square. We know that about, if it had been 1 by 1 plus z square, we know it would go, as we did in our previous video. But with cos az in the denominator, let us first examine cos az. We know that cos az is equal to e raised to I az plus e raised to minus I az divided by 2. Now let us look at this point, say point P, where it is coordinates or IR. R is the radius, and then since this point is located on the imaginary line, so its coordinate is IR. So if I take this, let me take this part of e raised to az minus I az e raised to this part e raised to I. Its value at this point will be minus I a z will be IR. Z will be IR there. That is, it will be e raised to, now I into I is I square, that is minus 1, into this minus, that is plus AR. And now see, if when you let R go to infinity, this will not go to 0. This will also go to infinity. Okay, now if that happens, then this will not converge. You cannot then evaluate, you cannot take this equal to 0. That is the problem. So how do we solve this problem? We cannot escape this problem. For example, by suppose had we taken this lower loop, then the same point would have been minus IR. But at that time, this e raised to I az term, that would blow up. That would go to infinity. Now, as you can see, e raised to my z is minus IR, that is minus 1 into minus, that is plus AR. So this then becomes a problem for us. What to do? How to handle this? How to handle this is there is an easy way out. That is, instead of evaluating this integral, I is equal to 1 by 2 integral. Instead of evaluating, let us go back. Instead of evaluating this I dash, let us evaluate e raised to I a z. That means this in place of a cos e raised to I a z. Why you will see yourself, because that will converge, that will go to 0. Now e raised I then have, suppose my integral is this, I dash is equal to 1 by 2 loop integral of e raised to I a z divided by 1 plus x square z square dz. Now first of all, let me find residue of this. Now its residue will be equal to fz. We have fz is equal to e raised to I a z divided by 1 plus z square. In that place, 1 I can write z minus I into z plus I. We have done this all in our previous question, and I will rely upon that. This is the this is fz. Fz is this. Now in order to find it is residue at z equal to I, z equal to minus I will not bother about that, because that is not within my loop. My loop goes from minus or to plus or to c or back to minus or. The lower part of the loop is not included in my question, in my c. Now so z is equal to minus I is not that singularity that for me, for this loop. Okay, now z equal to I, what will be the singularity factor? That is z minus I. So we multiply this by z minus I into fz. That will be e raised to I a z divided by z plus I. Now since it is a simple pole here, so what I have to do, I have to take limit of this. Limit z tends to a z minus I z minus I into fz is equal to this is the residue. Now that is equal to z minus I. Z is to be taken equal to, this means I have this equal to limit z tends to I e raised to I a z divided by z plus I. This factor, that when I substitute it there, it gives me e raised to I a z is equal to a, that is z equal to I, not a, sorry, z equal to I, singularity is I, not a. E raised to I a into I divided by z plus I, that is I plus I. That gives me e raised to minus, because I square e raised to minus a divided by 2i. That is equal to e raised to minus a divided by 2i. That is equal to 1 by 2, or I can take it here, or let me keep it as it is. This is the residue. Now if I substitute this residue back into the value of j here, j is this. We usually write j for this. Instead of I dash, let me write j is here. If I find it, if I substitute it there, residue, then the value of j will be then equal to 1 by 2. This is, sorry, 1 by 2 into, now 2 pi I into residue, 2 pi I into residue is e raised to minus a divided by 2i. I and I will cancel, 2 and 2 will cancel, we will get pi e raised to minus a divided by 2. This is the value of j. Now, having found this j, then what I do, I will keep it here because I will need at the end, I will need this. So it is pi e raised to minus a divided by j divided by 2. But I also know that j can be broken into two. So this integrals. One, this is the loop. This is minus r to plus r. This is cr, and I know that j is equal to, j can be now decomposed into two. One is minus r to plus r, a real integral minus r to plus r, that is e raised to, let's go back about j. J is 1 by 2. First it is 1 by 2 e raised to I z, 1 by 2 e raised to I a x divided by 1 plus x square dx. Along this real axis, it will be x. Now, along that 1 by 2, 1 second, I have 1 by 2 integral, so not closed now. Loop this line integral along CR of e raised to I a z divided by 1 plus z square dz. Now, we have now to see the behavior of this as r goes to infinity. As r goes to infinity, we know that for if I had just 1 by 1 plus z square, we know I have calculated that in my previous question, and I will rely upon that. That is, we can write now this integral, this CR integral. About this, I am talking about this CR integral. CR, I mean this integral. CR 1 by 2 CR e raised to I a z e raised to I a z divided by 1 plus z square is equal to dz. Now, so far as this factor is concerned, e raised to I a z, I can write it as e raised to I a. In place of z, I can write x plus iy. Simply because it is a complex number and complex number can be written as this. Then I can write it as equal to I a x, okay, into plus or see I that is minus I, minus a y, I a x minus a y. That can be written as, further it can be written as I e raised to I a x into e raised to minus a y. Now, so far as e raised to I a x is concerned, using this Euler's theorem, we have cos ax plus I sin ax into e raised to minus ay. The same cannot be written for this because it is not complex. You don't have I here, so you have this. Now, modulus of this is equal to 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 modulus of this and modulus of this. You can separate modulus in products. Now you have, what is modulus of this? That is simply modulus of this is root cos square ax plus sin square ax, that is modulus of this, into modulus of this e minus ay. But this is 1, so we have modulus of this equal to e minus ay. Now that is equal to 1 by e ay. A is positive and in the upper half y is also positive. This is the loop minus r to plus r, and this is the upper loop CR. In CR, y is positive. It is in the upper half, so y is positive. So y lies between, we can say y lies between 0 and 1, positive. A is positive. Now we can expand it using this expansion series expansion of e raised to x. So I can write 1 plus e, 1 plus ay plus ay square plus dot dot. Now, since a is positive, y is positive, this means that this whole is greater than 1. This whole is greater than 1. Now, when denominator is greater than 1, this means that the ratio or the quantity must be less than 1. So, ultimately, we have reached this conclusion that this whole e raised to I a z is less than 1. Less than 1. Because the denominator turns out to be greater than 1. So, this is less than 1. Okay, this I is at, and so far as this rest is concerned, we already know. So 1 by 2 integral CR e raised to I a z divided by 1 plus z square dz. That is, if we take modulus of this all, modulus of this, it turns out to be less than modulus of this. We have modulus of this 1 by, sorry, so let me once again write it here. I have now this with me. I have 1 by 2, 1 by 2, 1 by 2. Just 1 minute. Just a minute. So I have this situation, then this is. Now I am writing this now. I have I have this integral e raised to what was it? It was integral was e raised to I a z mod e raised to I a z. First, let me put 1 by 2 here. E raised to I a z is, or I can keep this there because when something will go to 0, multiplying it by 1 by 2 hardly matters. E raised to I a z divided by 1 plus z square dz is less than or equal to this our this quantity with which it is less than or equal to this 1 by z square, 1 by z square, because this in this numerator turned out to be less than 1. That is why this is the result. Now this is, since this numerator is less than 1, the whole integral is less than this. And then we know about this, we know about this, its behavior as r tends to infinity. We know it goes to 0 because it has that, as we know that total length is pi r multiplied by 1 by r minus 1 into r square root r square plus 1. These are the minimum values. These minimum value of 1 by z minus a and 1 by z plus a. We have discussed that in previous course. I will not touch it. And then when r goes to, now let r tend to infinity. As r tends to infinity, this becomes pi r into 1 by r. You can ignore this. Now r square, root r square, that is r, 1 r cancels 1, this pi by r, but as r tends to infinity, pi by r goes to 0. Hence, the whole this integral along CR goes to 0 as r tends to infinity. So we are left with just one integral, and that is we had start with this. Now let us now finish this by redrawing this minus r plus r. Then we had this I here, minus I here. This was CR, and this was minus r. Now we had original integral was I is equal to, that was original integral. that was that was 0 to infinity cos ax divided by 1 plus x square, or x square plus 1, x square plus 1, okay, dx. In order to evaluate this, first what we did, we extended this limits, infinity minus infinity to plus infinity cos ax divided by x square plus 1. Then we converted this into a contour integral. Instead of this, we considered this contour integral, that was j equal to, it was 1 by 2, j is equal to contour integral is divided by j 1 by 2 contour integral c along path c cos a z divided by z square plus 1 dz. This was the contour integral, and then what do we, and c we choose this loop, this as shown in the figure. And then what we did, we found the value of j first through residue, through residue, using those residues, and we found it to be it was pi by 2 e raised to minus a yes, pi by 2 e raised to minus a, this including this 2. Then we broke this into two, that is, one is 1 by 2 minus infinity to plus minus or plus, it was minus or to plus or cos this. Sorry, we first of all what we did, we did not convert this into it. Instead of this, we considered this e raised to I a z. Instead of cos, we considered this. Now then we broke it into two, 1 by 2 minus or to plus or e raised to I a x divided by x square plus 1 dx plus 1 by 2 e raised this c or e raised to I a z divided by z square plus 1 dz. That means one part from minus or to plus or another from this. Now we saw that as r tends to infinity, we let r tends to, this goes to 0, this whole goes to 0, we are left with this. So we have j equal to, finally we got j equal to 1 by 2 and then 1 by 2 minus infinity to plus infinity minus infinity to plus infinity, that is equal to then e raised to I integral e raised to I ax divided by this integral e raised to I ax divided by this 1 plus x square plus 1. But we want only cos, so we can write it as 1 by 2 integral minus infinity to plus infinity e raised to, that is cos ax plus I sine ax divided by x square plus 1 dx here. I want only this part, the real part. I can ignore this imaginary part and separating this into real and imaginary part. So I have finally got this. I have 1 by 2. In its place, I will write 1 by 2 minus infinity to plus infinity cos ax divided by x square plus 1 dx is equal to. Now, what is the value of this? Value of this was value of this was 2 pi by 2 e raised to minus a, pi by 2, so j is pi by 2 e raised to minus a, e raised to minus. Since it is real, I have equated real parts with real part of this with real part of this. Real part of this j is value of j is this, so real parts are equal. I can cancel 1 by 2, I got my answer. But again, that was not my integral, it was 1 by 2, so I will have to keep this there. It is pi by 2 e raised to minus a. That is the solution. Next, we have another type of problem that in which you have some integral like this, integral 0 to something like this, integral 0 to 2 pi, then a function of sine theta, a function of cos theta. Integral can be inside integrand is a function of sine or cos. I can write, so for example, as an example, let me take this 4 plus 5 plus 4 sine theta d theta. This I can write this as I is equal to now contour integral. I am changing it into contour integral. C 4 by 5 plus 4 sine theta d theta. Okay. Next, what I do, I convert this sine theta into, I write it as C 4 by 5 plus 4 sine theta. In place of sine theta, I write e raised to I theta minus e raised to minus I theta divided by 2i. Now d theta. Since sine theta is equal to e raised to I theta minus e raised to minus I theta divided by 2i, I can easily calculate this derivative d theta here. I can write it as sine theta, that is sorry, I can do one thing that here, that is if I substitute z is equal to, let me do one thing. I substitute z is equal to this substitution I will use for this integral. Z is equal to e raised to I theta, then dz by d theta. Dz by d theta will be equal to I e raised to I theta. That will give me dz is equal to I e raised to I theta d theta. But e raised to I theta is equal to z. So I have dz is equal to I d theta. Here you must have I z, e raised to I theta is z. I have chosen a unit circle for this contour integration because I am taking or. Actually you have to write z is equal to or e raised to I theta, but I am taking or equal to 1 here. So I am actually choosing this as a unit circle centered at origin. Now, having done this, next I do this thing. That is, I go for this C 4 divided by 5 plus 4. This is z e raised to I theta, that is z, and minus e raised to minus I theta, that is e raised to minus I theta is 1 by e raised to plus I theta, that is 1 by z minus 2i, divided by 2i into d theta. D theta is d theta, as you can see, it was dz is equal to, so d theta is you have to work in reverse order, that is d theta is equal to dz by iz from here, dz by, so I write here dz by iz. Good. Now 2 ones are 2, 2s are 4, and then with a little bit of this that I will do here, I will be doing it here. I have this space, some space left, so I is equal to integral. See what I am going to do, I will first multiply this by, this will be 5i, and at the same time I will get denominator I here, that will go to numerator, so I will have 4 and I divided by 5i, okay, plus 2 z into, now 2 we have then inside z into 1 by z, that is z square, minus I minus 1 divided by z, divided by this z, okay, then dz here, dz divided by iz. Now this I will cancel with this I. So similarly, this z will cancel with this z. So I am left with this simple, a little bit simpler expression, and that will, I will take that here I is equal to integral integral 4 and then 4 divided by 5i, okay, 5i plus 2 z square minus 2, multiply this 2, multiply this z square minus 1 with 2, that's 2z square minus 2, 2z square minus 2, 2 plus 2z square minus 2, then dz. Now that gives us 4 can be taken out, so you have 4 integral. This can be now written as, one can write this as 2z square plus 5 I 5i 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 plus minus 2, which can be written as plus, this minus 2 can be written as plus 2i square, because I square is that minus 1. There is a little that mistake that we have committed, that is this here. You can see when we got z here divided by z, we simply cancelled it with this z. That's wrong. We had to multiply this with this first, then get a common denominator of these, that could be multiplied with this. We can rectify this problem here by multiplying this by z. So it is 5zi or iz, 5iz. Okay, I can then do this as like this, 1 by 2z square plus, I can write this as 4iz plus iz plus 2iz, 2i square dz, 5iz. Okay, then that is 4 integral 1 divided by you have now 2z square here, you can take 2z common, you get z plus 2i, correct, plus here you can take I common, you can get z plus 2i dz. Now that gives us 4, this contour integral c, 1 by 2z, z plus 2i, into z, 2z plus I, that gives us dz, then dz. Then what we have, what else do we have? Yes, this we know how to solve. We have to get the residues and then evaluate this much. The procedure after this is quite simple, easy, that you know, and I will leave that to you. Okay, this was about different types of problems that you get on this residue theorem. In our next video, we'll take up a new topic, that's Fourier analysis, Fourier series, and that related topics. So, but before we end up this, one thing that I wanted to tell you is that you saw in this video, you had one, first was Cauch'ys this integral theorem, CIT, Cauch'ys integral theorem. Then came Cauch'ys integral formula. Then came Cauch'ys generalized Cauch'ys integral formula. Then came this Cauch'ys residual formula. Cauch'ys residue formula. There is one more, something more there, that is Cauch'ys principal value theorem. In fact, this man Cauchy, such people really those are amazing people, in the sense that there is so much in their name, there is so much after their name, so much in mathematics. I have not seen many mathematicians who have so much in their credit as Cauchy. Although Cauchy, it is more surprising that Cauchy was basically a civil engineer, and then this civil engineer While he was an employee, he worked as an engineer. He was very much interested in mathematics and physics, and he later on he became a teacher of mathematics, a teacher of physics, and he has done so much of research in these two fields, and including engineering as well, astronomy, engineering, physics, mathematics, all this. Such great men, they really deserve our salute. So Cauchy's integral, see, we let us now put things in the right place. That is, use this Cauchy integral theorem when Cauchy integral theorem tells us that loop integral of a loop integral of this, say, fz dz is equal to 0, provided the loop, this curve does not enclose any singularity. If there is no singularity, then this is equal to 0. Now if there is one singularity, then the integral is not equal to 0. It's equal to 2 pi I f z fa. Now this is Cauchy's integral formula. Then there is Cauchy's generalized Cauchy's. This is for, I should say, this is for, I should write it, no singularity case. When there is no singularity. Okay, when there is one singularity, it's one pole, simple pole, one simple pole only applicable to that. Now here, this is a pole of order of pole of, just a minute, pole of order 0, sorry, pole of order more than 1, greater than 1. Okay, then Cauchy's residue theorem, that is multiple singularities, multiple poles or multiple poles. There is something more about this, that is beyond this, that is Cauchy's principal value theorem. That is a novel, a very interesting thing of handling integrals with singularities. Suppose there is a singularity. Suppose there is singularity somewhere here. Let it be at, say, z equal to a. There is a singularity. Cauchy's principal value this theorem, that is a technique for extracting this singularity and throwing it out. That means it's a sort of surgery. It performs a sort of surgery. That, but that is not in our syllabus, and so we need not bother about that. Okay, then thank you for this, for all your cooperation in this complex analysis. We now move on to Fourier analysis in next video. Thank you.